Okay, so we're on our last assumption now, where we're testing whether the variances are homogeneous. And what this means, it's just kind of very difficult language for the distribution of our data needs to be similar. So the distribution, woo, there goes the mouse again. The distribution of each of our groups needs to be somewhat similar in order for ANOVA to be calculated correctly. Okay, so the way that we need to check this is we need to run a Levene's test. And it's just another statistical analysis, just like a one-way ANOVA or a t-test, but it's called a Levene's test, that will provide us a p-value for that particular test. And if that p-value of Levene's statistic is greater than 0.05, it tells us we can assume the variances are equal, okay, which means not different, which means homogeneous. Okay, so what we want to see when we run this test is that our p-value for Levene's statistic is greater than 0.05. Now, how do we run Levene's test? So you can go over to Analyze, back to SPSS, and you can actually go ahead and run your ANOVA, and Levene's test is one of the options within ANOVA. So if we go to Compare Means, down to one-way ANOVA, our dependent variable, what's being measured, is self-efficacy. Our factor, or our independent variable, is group assignment. Okay? And so if we go to options, you'll see homogeneity of variance test. Okay, and that's the option we need. But just so we can go ahead and finish out our analysis and then go back over to our 9 steps, we also want to click descriptives because that gives us a little bit of information on means and standard deviations. And then also in ANOVA, you're going to want to run a post hoc test, and I'll talk about that in just a bit. You're going to want to run a Tukey post hoc test. So we're going to click OK. And here's our output. What we want to check right now is this box, and we'll get to all these other details in just a bit. But this is the box that shows us the test of homogeneity of variance. Notice it's the Levene statistic. The actual statistic for the Levene's test is 0.801, but what we're interested in is the p-value. Remember, SPSS does not use p-value, it uses significance, and our p-value is 0.457. So if we go back over here, I always like to include that in here. So our p-value for Levene's test is 0.457, which is greater than 0.05. So we can assume the variances are equal, which is the same as homogeneous. So we are okay on this particular assumption. So we considered the p-value of Levene's test. And I always just like to include that p-value so that you can, if you're going back to study again, you can see where it came from. Okay? So we have met all of our assumptions for a one-way ANOVA. Whew! That's the long part of doing the ANOVA. Now we're ready to do our hypothesis. Remember, we have a null hypothesis, which statistically, this is what we're testing. And our null hypothesis typically has a no or a negative connotation. There will be no difference. Remember, difference is either a t-test or ANOVA. And self-efficacy scores. Self-efficacy is our dependent variable of individuals, if I can spell individuals, in the 3 care groups, because the 3 care groups is our independent variable. This is our dependent variable, self-efficacy scores. This is our independent variable. Okay. Then our research hypothesis, or our alternative hypothesis, or what we want to really find out, is there will be a difference in self-efficacy scores of individuals in the 3 care groups. Let me fix my self-efficacy here. Because who would want to do a study and find out that they're not different? So we really want to know, we want to make sure they are different, but we have to test that they're not statistically in order to find out that, okay, then we think they are, okay? So, okay, undo that. We're going to buy Dr. Slining a new mouse at the end of the semester. The test statistic, we are doing a one-way ANOVA. And just in case you've missed it at some point, ANOVA stands for Analysis of Variance. Okay, so it does, that's why it's all capital, because it does actually stand for something. Decision rule. I don't think I have to say anything about this at this point. You can draw it in your sleep now. Your roommate can probably draw it in his or her sleep. So I'm just going to let that be here. You know what to draw here, and you know what it means. So we're ready to calculate our test statistic. So in order to do that, we've already run our analysis. So I'm going to describe the output a little bit for you since we've only talked about this part of the output. And then we'll go back over and put the information in. So to look here, this is our descriptives for our entire sample. It's telling us we had 11 individuals in our first group, and they had a self-efficacy group mean of 134.73 and a standard deviation of 22.703. And then something's always cool to me to look over and go, okay, this was the lowest self-efficacy score for this group. This was the highest self-efficacy score for this group. And then same thing for group 2 and for group 3. And then what's also really interesting is to look at the total. Okay, so that's our descriptives. If we look here, the ANOVA output, this is where we're going to find most of our information for step 6 and 7. So ANOVA tests for a difference among the groups. And so we have 2 degrees of freedom that we have to use here. One for testing a difference between the groups, and one for testing a difference within the groups. So we use both 2 and 34 to report our degrees of freedom. Our F, which is the statistic that represents ANOVA, it's 7.747 for this particular analysis, and our p-value is 0.002. So if we go over to step 6, we're going to say that F, and F is capital for ANOVA, whereas T is lowercase for t-test. F with degrees of freedom of 2 and 34 is equal to 7.747. And just remember, we got this from this ANOVA table, our degrees of freedom and our F. And now we're going to go put in our p-value for step 7. Our p-value is equal to 0.002. And because it is less than 0.05, based on our decision rule, we know that we reject the null hypothesis. So if we reject the null, we go back up here, we say we don't want this one, so we must want this one. That's why we have 2 hypotheses. If we don't accept one of them, then the other one we think might be true. Ooh, I did not copy it. Let me go back. This mouse is getting me. Here we go. So we're going to say there may be a difference in self-efficacy scores of individuals in the 3 groups. And again, Dr. Slining and I, or any other person that reads research, is going to go, well, how do you know that? And so you have to provide the statistics to substantiate the conclusion. Otherwise, we're not going to trust you. We want to see the numbers. We want to see the evidence. And so I just got the information for my degrees of freedom and F value from step 6. Got my P value from step 7.
Check your end quote. Starting parentheses right after.
Oh, sorry. Didn't hit my shift. Sorry. Thank you, Dr. Slining. Okay. Now, based on the book, again, the book provides a much more comprehensive explanation of this, and that's really nice when you are reading things in journals. You want to know more than there may be a difference. So let's look and see what the book tells us. It will, if you look in your book, it says, we computed a one-way ANOVA comparing self-efficacy scores of participants in 3 care groups. A significant, and we know it's significant because we rejected the null, Okay, so that showed us it's statistically significant. Difference was found among the groups. Again, provide the evidence as to why you say there's a significant difference among the groups. So again, you have to provide the F. Yes, again. And yes, I did my parentheses wrong again. I don't like Dr. Slanning's keyboard either. We obviously get used to our own computers. Okay, so we have our statistical statement there after saying that we have a significant difference. Now we want to get into that post hoc test that we talked about just a minute ago when I was running the analysis. If you go back over to your SPSS output, you'll see that you have a post hoc test. Post hoc means that you run this after post you find that you had a significant difference. So with t-test, you only have two groups, and you go, okay, they're significantly different. You can look at the means and find out which one's higher or lower. Well, with the one-way ANOVA, you have more than two groups. So you can't just go to this descriptives table and look to see, are these different? Well, what we know is that this 129 and 134, yes, to our eye, they look like they may be different. But statistically, is that a big enough difference to be different? I know, crazy question to ask, but that's what, as statisticians, that we ask. And so we don't know that. We know there's a difference somewhere. It might be between this and this. It might be between this and this. It might be between this and this. We don't know. We can't tell by just looking at the means. So post hoc helps us know which mean differences for the groups are statistically significant. And so we run a Tukey, HSD, honestly significantly different. It's a very conservative calculation of significance for mean differences. So let's look at this for just a second. We've got our group 1 here compared to our group 2, okay? And this is the mean difference between groups 1 and 2. You notice up here it says I minus J. So it's saying it took the mean for I and subtracted the mean from J. And we have a positive number here. So that means this mean was higher than this mean because we have a positive number based on this difference. And then if you go over to the significance section, you'll notice this difference is not statistically significant because it is, the p-value is greater than 0.05. Okay, so if we look at group 1 compared to group 3, our mean difference is 31.881. Again, who has a higher self-efficacy? Group 1, because it's I minus J. And this, excuse me, is significantly different. It is statistically significant because this p-value is less than 0.05. Then if you go to the next one, you're comparing groups 2 to 1. We've already done that up here, 1 to 2. But now we get groups 2 and 3 compared. So here we see the mean difference is 26.462. Again, it's a positive number. Group 2 must be higher in self-efficacy than group 3. However, this is not statistically significant. It is not a significant difference. Oh, it is. Sorry. I was thinking it was 0.1. I'm sorry. It is a significant difference. It is statistically significant because it's less than 0.05. Sorry, it is significant. Okay? And that's really all you have to look at. This bottom one compares group 3 to group 1, which we've already done, 1 to 3, and compares group 3 to group 2, which we just did. And it is significant. So you don't have to look at that bottom row. So all of that to come back over here, darn book gives us so much information. And we say that we did a Tukey's, it's like turkey without the R. HSD was used to determine the nature of the differences among the groups. And now we're going to report what we found. This analysis revealed that group 1, if we go back over here, group 1 had a higher self-efficacy than group 2. Okay, so group 1, and we'll put its mean and standard deviation. So this is where you have to really go digging for information. So go back over here and find the mean of group 1, 134.73. Okay. I'm going to say mean. And the standard deviation, if you go back over here, is 22.703. 1 was, or we'll say scored, higher than group. Go back down here and see what we're saying. So we're saying group 1 was higher than group 2. Okay? And so now we have to find group 2's mean, 129.31. And the standard deviation, is 24.411. Okay, now you'll notice I did not say it was significantly higher because it's not significantly higher. Okay, if we go down here, it's 0.815. Okay, so this analysis revealed that group 1 scored higher than group 2, and you don't say that it was significantly higher. Okay, then we're ready to do groups 1 and 3. So group 1, you've already stated the mean and standard deviation, so you don't have to state that again, scored significantly higher than group 3. We have not put group 3's mean and standard deviation, so we've got to go back over here and get it. It's right here. Group 3 mean is 102.85, and the standard deviation is 17.276. Okay, now that was significantly higher. So you want to provide the p-value for that significant difference. And you find it by looking at your post-hoc. So group 1 was significantly different from group 3, and the p-value was 0.003. Okay, and so you can provide that. Always do it close to the term significant or higher. So it was, let me go back and get it, 0.003. Okay, so we've compared group 1 and 2. We've compared group 1 and 3. Now we're ready to do groups 2 and 3. And what we remember is it was significantly different. So we can say group 2 scored significantly higher than group 3. We don't have to report any of the means or standard deviations because they're already in this explanation. What we do need to report is the p-value. So again, 2 and 3, the p-value is 0.010. And so we're going to put it somewhere close to the significantly higher. P is equal to 0.010. Okay, so what we've done here in the more comprehensive discussion of our conclusion is we've said we computed a one-way ANOVA looking at self-efficacy scores of participants in the 3 groups, and we found that there was a difference somewhere. That's what ANOVA tells us, if there is a difference, not where the difference is. The Tukey's HSD helps us to know where those differences are. And so then we explain what we found from that Tukey's HSD, that groups 1 and 2, although 1 was higher than 2, it was not significant. However, groups 1 and 3 and groups 2 and 3 were significantly different. And so if you go back to the question that was asked, determine if there is a difference in self-efficacy based on group assignment, we can confidently say we think there may be. And we think that difference is between groups 1 and 3 and 2 and 3. but not between 1 and 2. Okay? That is your one-way ANOVA analysis.